Here I'm going to work through solutions to an AP Calculus free response question. This one happens to cover units 4, 5, and 7. During a chemical reaction, the function y equals f of t models the amount of a substance present in grams at time t seconds. At the start of the reaction, t equals 0, there are 10 grams of the substance present. The function y equals f of t satisfies the differential equation dy over dt equals negative 0.02y squared. That's the setup for the problem, and then we have 4 questions that we're going to answer, A through D. And I'll address each of those on a separate slide. So let's get started. For letter A, they ask us to use a tangent line to the graph of y equals f of t at t equals 0 to approximate the amount of substance remaining at time t equals 2 seconds. We typically call this a linearization. And so when we set up that linearization, it usually looks something like this. L of t, our tangent line, is f of a. And then, of course, for us, a is t equals 0 plus f prime of a times x minus a. And as I mentioned, for us, a equals 0, right, because that's our time. So my linearization, oops, I wrote x here. I guess I should stick with the correct variables. This is a t. So we're using the letter t instead of x in this function. So our tangent line approximation function is L of t equals. So f of 0, that's the amount of substance at times t equals 0, and they already told us that was 10 grams right there. So that's 10. The derivative at 0 we can find by plugging in y into the derivative function. So I'm going to do negative 0.02 times 10 squared. And maybe I should write that out. Negative 0.02 times 10 squared, which is 100. That's my f prime, that's my slope. And then we'll have t minus 0, which is just t. So that approximation, that tangent line is, that's going to be negative 10 minus 100 times 0.02 is 2, 10 minus 2t. And then they want us to use it to approximate the substance remaining at t equals 2. So I'm going to take 2 and plug it into my new function here. And so that's going to be 10 minus 2 times 2, which is 10 minus 4, which is 6 grams. So there's 6 grams of substance, approximately 6 grams of substance at time t equals 2 seconds, based on a tangent line approximation, which we've been calling a linearization. Okay, just double checking to make sure I didn't screw anything up on this one. It looks good. So let's move on to the next slide and we'll attack letter B. Letter B asks, using the given differential equation, remember that's this one right here, negative 0.02 times y squared. Using the given differential equation, determine whether the graph of f could resemble the following graph. And we're going to give our reasons. So in letter B, we need to see if this graph could resemble the graph of f. Now remember, we don't actually have the function f explicitly defined for us, at least not yet. But what we do know is that the derivative, dy over dt, can be found by this function. And you'll notice that y squared is always positive, or 0. Y squared is greater than or equal to 0. And that means that negative 0.02 times y squared is always going to be negative or 0. So I am concluding that dy over dt is always less than or equal to 0. So we are either decreasing or flat or constant. Okay? Now, take a look at this picture here. This graph is decreasing here, but then at some point where t, out here at t is greater than 0, but at some positive number, the graph starts increasing. So this graph cannot, will not resemble the graph of f. This graph will not resemble the graph of f. Because it has a section, an interval where the function is increasing. Oops, that's supposed to be a C. That because the graph is increasing on an interval. We don't know the exact interval because there's no labels on the graph. But we can say that it's increasing on an interval. You got to spell interval right, though. Okay, so in general, my answer is that the graph will not, oops. Man, I'm having a bad go at this one, aren't I? Let's try the highlighter. I'm saying that the graph will not resemble f. We were asked to say if this graph could resemble f or if f would resemble the graph, and the answer is no, because we have determined that our derivative is always either negative or 0. Okay, hopefully if you're answering a question like this on the AP test, you'll be maybe a little more articulate than I am. But I think you understand the gist of this problem. Let's see if we can do a little better on part C on the next slide. So part C says to find an expression for y equals f of t by solving the differential equation, dy over dt equals negative 0.02y squared, and we have an initial condition of f of 0 equals 10. So we're basically going to do separable differential equations and then solve for c. So I'm going to make a note that f of 0 equals 10. That's my initial condition. Can't write. Picking up right where I left off on the last slide, I guess. Let's start with that differential equation, dy over dt equals negative 0.02y squared. So remember, the technique for separable differential equations is to get all the y stuff over here and all the x stuff over here. And then we're going to do the antiderivative on both sides. So I'm going to, divide by y squared. So that's negative, that's y to the negative 2. Come on, man. Okay, so y to the negative 2. I'm going to multiply dt over the other side. So this is y to the negative 2 dy equals negative 0.02 dt. Remember, we're going to integrate both sides. So I'll slap an integral symbol in there. And we'll do the antiderivative. I have to use the power rule on y to the negative 2, so that's going to be negative 1 y to the negative 1, better known as negative 1 over y. There's a plus c there, but I'm going to collect it with the other plus c on the right-hand side. The antiderivative for negative 0.02 is negative 0.02t, and then there's my plus c. And then we usually solve for y, so let's do that. I'm going to multiply by negative 1, and then do the reciprocal. So y is going to be 1 over 0.02t, and then plus c minus c, it's the same thing. I'm just going to put plus c. When you multiply this placeholder c by negative 1, it's still all the real numbers, so it's still c. We've had that discussion before. It doesn't follow the rules of algebra, but that's okay. Now, we need to do our initial condition, so I'm going to kind of move my line of writing here over there. I'm going to plug in 10 for y, right, because that's my function value. And then I'm going to plug in 0 for x. And so, or t, 0 for t, so that's going to be negative 0.02 times 0 is still 0, plus c. So 1 over c equals 10. That means, that implies that c equals 1/10. And since we've been writing decimals here, I'm just going to write 0.1. Okay, so let's put this function together. F of t equals 1 over 0.02t plus 0.1. So that's the function, but we generally don't write fractions with decimals in them. So we can clean this up. If this were 0.01, I would just multiply the top and bottom by 100. But since it's 0.2, I'm going to multiply the top and bottom by 50. So this is a form of 1. We're allowed to do that, but this is just how you clean up these decimals. So this is going to be 50 on top. Oops, I guess I'm going to write this in red. And then 50 times 0.2 is 1, so that's just t. And 0.1 times 50 is 5. So this is a cleaner way to write this function f of t. F of t equals 50 over t plus 5. And this is the function that fulfills that differential equation with that initial condition. I like those problems. Okay, just double checking things. I think I've got it. Let's go to the next slide and we'll wrap this one up with letter D. So letter D is going to make us think a little bit. Determine whether the amount of the substance is changing at an increasing or decreasing rate. So there's a lot going on here. This word changing, that has to do with the first derivative, but we want to know if the first derivative is changing at an increasing or decreasing rate. To me, that implies the second derivative. So let's see if we can examine that and answer this problem. We know that the derivative is negative 0.02y squared. So we can just differentiate again implicitly to get the second derivative. That would be bringing the power down, so it's negative 0.04 y to the first power times the derivative of y, which is dy over dt. And we know that that is negative 0.02 y squared. So this thing simplifies to, oh my goodness, a positive 0.0008 y cubed. Now, a couple of things to note. Just remember from the last slide, we know that f of t is 50 over t plus 5, and we know that t is greater than 0 because it's seconds. That means that this y is always going to be a positive number. There's no way to make this thing negative if t is greater than 0. So from that, I have determined that dy over dt2, the second derivative, d2y over dt2, is greater than or equal to 0. Actually, it's just greater than 0, right? Because I can't make 0 out of that thing either. Okay. And since this is greater than 0, this is increasing. So the amount is changing at an increasing rate. The rate, which is the first derivative, is increasing because the second derivative is positive. So in a nutshell, I'm answering increasing for this problem because of the facts that we presented over here on the left. Okay, lots going on in this problem. We worked obviously with differential equations, but also with linearization and tangent line approximation. So some good concepts included in this one. Keep up the good work. You know where to find me if you have any questions. Take care.